Hi, I'm Priya and I'm one of the optical designers at PNP Optica. In this video, we'll take you on a tour of our optics labs where we build the core components of our systems, which include the spectrometer, lights, and detector module. So we'll show you how we make sure this complex system with a sophisticated technology is made ready for the plant and made easy to maintain for our clients. So let's go and see how it's made.
Hi, I'm Alan. I'm a software developer here at PPO, specializing in industrial cameras, frame grabbers, and the camera interface to our software and in the system. The cameras, when we get them, they're pretty expensive near-infrared cameras, and they're idiosyncratic, so they need some testing and checking when they first arrive. And I do some sanity checks on them before passing them over to the optics group to make sure that they're ready to run our protocols and work in our machines with all their functionality. Some of the tests that I run here are looking for bad pixels on the camera. When we first onboard a new camera, we have to make sure that the performance is what we require. Make sure that the camera is running the same protocol and is going to work with our software. These are complicated software animals themselves, so we have to make sure that the firmware interface to the camera remains compatible with our software and will work in the system.
I'm in the optics lab and I have with me the camera after initialization. So after checking the sensor and making sure it is clean, I'll be starting with the linearity test. So what is linearity? We know that the fundamental process of a camera is to convert incident photons of light into electrical signals. So the linearity test is conducted to test and verify the camera's response to the incident photons. So whether it is linear, and if so, what is the slope of this line? So how do we do it? Let's take a look at the setup. We have light from a calibrated halogen light source entering the integrating sphere. The amount of light is controlled by the iris. The integrating sphere is coated with a special material so that light striking its walls undergoes multiple diffuse reflections. The light that comes out of the sphere is hence uniform. This uniform light from the integrating sphere is now collected by the camera that is mounted on a stable optomechanical fixture. This ensures that all the camera pixels receive the same amount of photons. We test the camera for 50 light levels to verify each of the over 300,000 pixels response. We then apply the linearity corrections for all the pixels, so all pixels respond the same for a given light level. Following this, we move on to the next step, which is using this calibrated camera to build a spectrometer. So let's go and see how a spectrometer is built. Now that we have characterized the camera, let's build a spectrometer. You can see that the spectrometer has been assembled here and connected to a computer. The spectrometer includes a slit followed by a lens tube, a grating, a second lens tube, and then the camera that we looked at earlier. The lens tubes can be moved within a reasonable amount to adjust for focus and field of view. The first step is to fix the spectral range of the spectrometer. I'm going to use an argon lamp because it emits discrete spectral lines. As I adjust the lenses, you can see that the lines coming into focus. You can also see the characteristic smile that we had discussed. I will now align the peak at 965 nanometer to a specific pixel position. This will be consistent across all spectrometer builds, making every PPO spectrometer build identical. Now that the spectral calibration is complete, we are going to adjust the spectrometer for its field of view. Now you can see there is an external lens to the spectrometer and it is placed at a distance from a target to mimic the PPO smart imaging system. The dark lines indicate the range within which I want the spectrometer to work, and with the halogen lights on, I'm going to again move the lenses. By doing this, I'm changing its magnification. I can see that the spectrometer is within the acceptable field of view and also in focus. So I will be locking this position down. The next step is applying corrections. We are going to start by looking at the smile. You will notice that the smile in itself is not symmetrical. We can fix it by gently rotating the slit around. After some patient work, the smile is now corrected. Now we will measure for keystone correction, which we had also discussed in the webinar. And here is the target. I'm going to take an image of the straight lines and apply a correction to it. Now that these tests are done, I'll do a final series of checks to make sure the spectrometer meets all the required parameters. And when I'm done, the spectrometer is now ready to be installed onto the PPO system. So let's go and see that. Hi, we just saw how a spectrometer is put together, how it is aligned. Now that it is aligned, we are going to put it on a frame. Here you can see the spectrometer, and you can see one more camera out here. This camera is going to see exactly the way our eyes can see, so the visible region, and the spectrometer here is going to see the infrared region. So the next question is, how are they both seeing the same scan line? So we have two mirrors here which are specifically coated such that this visible camera receives visible signal, and the spectrometer receives the infrared region of the signal. So the next step is to ensure that the camera, the visible camera and the spectrometer are looking at the same object, that is the same scan line. So to start that, here is the target with dotted lines, and it is set up on the table such that it is going to be parallel to the belt. And then I'm going to move the visible camera first and ensure that I'm seeing all the lines in its field of view. So to do that, I'm going to turn the lights on. Here I am adjusting the visible camera, and I'm moving it enough so that I'm able to see all the lines. I'm going to tighten it up here. And once this is tightened up, I'm going to move on to the spectrometer. And the spectrometer has some adjustment rings here, so I'm going to move that around until I see the dotted lines. So now that I have ensured that both the spectrometer and the visible camera are seeing the same scan line, which would mean they are going to see the object at the same time, the next step is going to be putting on the calibrated lamps. So Danielle is going to show us how the lamps are put together and how it's going to come back here and how we run our calibration. So on to Danielle from here.
Because the PPO systems use near-infrared spectroscopy, the type of illumination selected for the system are halogen lamps. Halogen lamps were selected because they emit a continuous spectrum, which means there are no breaks or missing wavelengths within the emission range. They also emit in both the visible and the near-infrared range, which are both necessary to give us the best possible data. PPO designs and builds halogen lamps in-house. They are specially designed to be interchangeable, easy to maintain, as well as repair. Multiple design features have been selected to ensure that the lamps are easy to align while minimizing the risk of the lamps becoming misaligned over time. So here I'm holding a partial lamp assembly where you can see the lamp internals. It's just missing the front cover and the back cover. But here you can clearly see both the reflector and the bulb. So the reflector shape was designed to allow for high alignment tolerances. And the bulb location is actually adjustable. So during lamp assembly, the bulbs are aligned so all lamps have identical lighting profiles. So here we have an example of a fully assembled lamp with the window assembly and the back cover installed. The window type was selected because it has a high transmission, both the visible and the near infrared range. The lamps were also designed to be washdown rated. Because these halogen lamps reach high temperatures during operations, the window material was selected to withstand the thermal shock and minimize the risk of cracking if the system is washed down right after it's turned off. Finally, the lamps have also been designed to make bulb changes as easy as possible. The window assembly can be removed from the back cover and the reflector assembly by removing the 4 screws from these threaded holes. And then the bulb becomes easily accessible and can be swapped. It's worth noting that the bulb change will not affect the bulb alignment, so swapping one bulb for another will result in the same identical lighting profile. Once the lamps are fully assembled, they're ready to be put on the system, and once that's done, your illumination for the system is ready to go. Priya has assembled our spectrometer and aligned both the visible camera and the spectrometer on our frame. And now that I've assembled all the lamps and the bulbs in each of the lamps, the next step is to put the lamps on the frame, which you can see here. There's 4 lamps, 2 on either side of our scan line. So once I have the lights on and the live display set up, I would have the lamps loose so that I can adjust the angle, and I would be checking in with the live display such that height I'm working at, the calibration light profile is maximized, similar to what we were doing during the bulb alignment. The final check before we can confirm that the light profiles are good would be to run a calibration. So keeping an eye on the real-time display of the calibration profile, I would adjust both sets of lights until I'm satisfied with the calibration profile, fix them into place, and then run a calibration. Now, to run a calibration, the first step is to close the shutter in the spectrometer and then take a dark calibration. Once the dark calibration is complete, I would open the shutter and take a bright calibration. After which, the computer would process the data and output a calibration report. There's one final test that we do here in the optics lab before the system is ready to be assembled on the machine itself. And that test is a test performed to make sure the spatial focus across the field of view is acceptable at all points along the field of view. So once we've scanned our spatial focus target, we'll come take a look at the data to review it. And once we approve it, the spectrometer and vis camera assembly is ready to be put in our waterproof enclosure. And once it's in the waterproof enclosure, we can put our entire frame onto the system itself, and it's ready to go.
We have seen the lights and spectrometers assembled and calibrated. The final step was to put our spectrometer inside our sealed detector module and then mount the lights and detector module onto the frame. Here we are in front of a PPO smart imaging system, where you can see that we have mounted the frame onto the system. The assembled PPO smart imaging system is then tested at our facility for your specific application before being shipped. PPO system is specifically designed to be easy for our clients to clean and easy to service and maintain in your plant. PPO's smart imaging system will ensure your products are high quality and safe when you deliver them to your customer. What's in your food?